Alright guys, my name is Ted Bailey and this is my video lab report for Lab 3, Black Hole Orbit. The general idea behind this lab was to find the mass of a black hole given data about a star's position. So, I imported the data into a Python code and plotted the points to visualize the motion. Then, I used my knowledge of Newton's second law to deconstruct the motion and find information about the force acting on the star. Since the force of gravity is all that acts on the star, the force of gravity equals the star's mass times delta V over delta T. Using the equation for the force of gravitation, I found the mass of the black hole to be about 3.56 times 10 to the 31st kilograms. When the code is run, you get a graph of the star's motion over time. Included are three arrows, dp/dt parallel in black, dp/dt perpendicular in blue, and fnet in yellow. As you can see, the star's orbit is elliptical. Also, in the zoomed-in picture of the force arrows, notice that dp/dt parallel points opposite the direction of motion. This tells us that the star's speed is decreasing. Now I'm going to quickly bring you through my code. First are the preconditions. The star's mass was given as 1.989 times 10 to the 30 kilograms, and delta T is 1 day, or 86,400 seconds, when T starts at 0. This while loop is used to create individual changes in x and y between two adjacent data points. These changes in position can be used to find individual velocities between the same 2 points. Next, we take two of these velocities. We'll call the first v initial and the second v final, and multiply them by the star's mass. We will call these momenta p initial and p final respectively. Next, to find the delta v and delta p, we simply subtract each initial value from the final value. Then we create a variable called dp/dt and set it equal to fnet, since the change in momentum over the change in time equals the net force on an object. dp/dt parallel equals the difference in magnitudes of two individual momentums multiplied by p hat, which is the direction of motion. Since dp/dt equals dp/dt parallel plus dp/dt perpendicular, dp/dt perpendicular equals dp/dt minus dp/dt parallel. That is all the code for one iteration of the while loop. Every iteration, the code will take in a new set of two data points and solve for the forces that must have caused the change in position. Finally, outside the while loop, after the last data point, the code will have solved for a force acting on the star at a given position. Since the only force acting on the star is the force of gravity, we can set fnet equal to the force of gravity. This means that fnet equals gmm over the magnitude of r squared. Solving for big M, which is the mass of the black hole, we find the equation that m equals fnet times r squared over gm. Finally, we tell the program to print the mass of the black hole after the code is finished. Now for the what does it mean and what if questions. How are the force vectors different from the momentum vectors? While the force vectors are equivalent to the momentum vectors in magnitude and direction, the force vectors are acting on the system, while the momentum vectors are observed changes in the system caused by the forces. That is, the momentum vectors are caused by the force vectors, but they are graphically identical. For the what if question, what would happen if we replaced the black hole with a different one in the same location? The motion of the star does not change, but can we calculate a different mass for the black hole? It seems that since we calculated the mass of the black hole based solely on the motion of the star and the position of the black hole, we could not detect a difference since those two variables remain constant. We would get the same data and therefore the same mass of the black hole.